কি করব হ্যাঁ এটা এলে স্টার্ট করব hello there are some questions on the units that I have followed the units that are generally followed in most of the advanced text and undergraduate text is called the Gaussian unit, which is what we have followed. You will see that most of the books that you will I have referred to like Ashcroft and Marmin or Kittel, they have followed these Gaussian units, and the conversion is extremely simple actually. It just depends on how you write this force equation between two charges. So, if you have two charges, then you q1 q2 by r square, and then you can put a constant here. Okay. Similarly, if there are two currents flowing, then I1 I2 by r into k m. Okay. So, this is how the two constants are used, and what you write for these constants decides which unit you are using. Of course, these two constants are related, and so this is F by L per unit force per unit length. So, these two constants are related by 2 K E equal to C square K M. Okay. And there are these quantities called mu naught and epsilon naught, permeability and permittivity of free space, which is related to C square by C square equal to 1 by mu naught epsilon naught mu naught. Okay. So, all these things relate these two unit systems. So, in Gaussian, for example, Gaussian we take K E to be 1, whereas in SI K E is taken as 1 by 4 pi epsilon naught. Okay. And that basically decides how you go writing these forces, and once you write these forces, then you can decide in which units you will represent things. So, there is not much of a difficulty in going from one unit system to the other. The main reason for this difference is that in the MKS unit there is one more quantity which is used, which is they define the current as something called an ampere, which is not done in the Gaussian unit. In the Gaussian unit one starts from the charge, and since charge is related to force, then you can express charge in terms of see here it is charge square equal to force into r square. So, force you can replace by the standard CGS unit and r square you replace by centimeter square, and then of course, then your q square is f into r square. So, dynes into r square, and then of course, you can find out what your dimension of q is. So, once you have q, then charge per time is the current. So, you do not need a new unit in current, whereas in SI unit there is a unit of current, and that current is called ampere, and once you have that, then of course, these other units follow from there. So, the charge and in Gaussian and charge in MKS or in SI have different dimensions, but that is not a problem. All you need to know is that this 1 by 4 pi epsilon naught in the Coulomb's law, in the sense that this is force between two charges, that takes care of everything. So, and similarly, then if you write Lorentz force, for example, F equal to Q E plus V cross B, this is in SI, and all you have to replace is Q into V cross B, and all you have to do is just write a V cross B by C in Gaussian. So, once you know that these are the two differences, you can just write everything else. So, there is not much of a problem in using Gaussian units. You can choose your units, I mean it does not matter which unit you write your answers in. So, that is one answer that that was asked, and this is the way one goes forward from. You don't even need to convert from one to the other, because most of the questions that will be asked will give you the unit and you just write the answer in that same unit. Okay. And in cases you are asked only the expression, then you do not need to bother about it. You know how force is written in Gaussian, you know how force is written in SI, and you just change one from the other. Whichever one you use, we do not mind at all. You can use any unit you like. Are there any other questions?
So they have sent that can I post my doubts or queries in comments? I mean I have sent you on the spreadsheet. So you can open
yes. Yeah, of course you can.
So
you send. Where is the spreadsheet?
The first tab.
Let us see where is the spreadsheet.
So the first tab in Google Chrome.
First tab is no. Yeah. So yeah, of course. Shall I write here?
No, sir. You have to live just tell them you can ask.
Yeah. You can ask your doubts, queries in the comment. That is not issue at all. Somebody asked about graphene, right? And the question about graphene is that why graphene and what is so special about graphene? What are the day-to-day implementations using graphene? And okay, so let me answer the first question first. Why graphene? Graphene has actually changed the way we do condensed matter physics in the recent past, and it is one of the major discoveries. As you know, it got a Nobel Prize also. The reason graphene is so important is that this is a system where it is a system where you have just a monolayer and it is a hexagonal lattice, and it has a spectrum, the E versus K spectrum, which is linear at 2 points in the Brillouin zone and close to 2 points in the Brillouin zone, and that makes it like a Dirac spectrum, which is a relativistic spectrum, and that has tremendous applications, that has tremendous implications also in terms of applications and all that. Graphene has the other properties, one of the highest mobility material, and it is therefore used as part of applications. For example, graphene transistors have been built and they are not yet in the market in use, but they are being considered for future applications. So, day to day implementation when graphene's applications are still coming out. For example, this is a material which is almost impenetrable, even helium atoms cannot pass through it. So, even hydrogen is finding it difficult to pass. So, if you cover a cylinder, a box for example by graphene, nothing can escape the box, nothing can leak out of a box. So, all kinds of applications are being discovered and people are making use of it. Some of them are quantum, some of them are even classical. So, we still do not know all of them, but the applications are enormous. I mean, it is one of the major discoveries of 21st century. What is the difference between indirect and direct recombination? I have not taught recombination in this course. Why do you want to get into it? There is nothing I taught. I have discussed direct and indirect band gap, maybe I have told, I have maybe mentioned, but not trapping. Trapping has not been discussed. Physical properties of graphene: optical, thermal, magnetic. Graphene is not magnetic as such, The optical thermal properties, what kind of properties you want to know depends on that. We will try to post some of these properties on the web. How does it act at room temperature? It is a semi metal if you think of it, because it has a Fermi point. So, the density of states exactly at the Fermi point is 0, but immediately away from that point the density is there finite, and so there is no band gap as such. So, it is like a semi, if you want to use a terminology, you can use a semi metal, and then of course, you can dope graphene and you can make a, you can raise the chemical potential at the Fermi level in either up or down. So, you can go into metallic side, in the electronic side or the whole side, and then it behaves like a metal. So, it is not an insulator certainly. Reference books on graphenes, there are many. So, we will post some of the books that are available, and there are also very good review articles on graphene, which we will also post. So, what is Wigner Seitz cell? Somebody has asked. Wigner Seitz cell is basically take a point in your in your lattice and find out all the points that are closest to that, closer to that point than any other points of the lattice. I mean, that is how you can define a Wigner Seitz cell. So, take any point on the lattice and find out all the other points in that lattice which are closer to, on the, not on the lattice, in the region. For example, you take a, let me just show you one example. Sorry. How does it go? So, let me just show you one example. So, let us take a square lattice for example. So, suppose I want to find out the Wigner Seitz cell corresponding to this one. So, look, there are other points in the lattice also. There are 3 other points which are near, there are many other points. Here is one, and so on. So, all these points are so these 4 points are the nearest neighbors. So, this one, this one, this one, and this one are nearest neighbors to that point, this point. Now, I want to find out the Wigner Seitz cell corresponding to this point. So, the definition is I will find out all parts of this region, all the region that is closer to this point than the other points. So, the nearest neighbors are these 4. So, all I have to bother about these 4 nearest neighbors. So, what I do is that I just draw this perpendicular bisector at the midpoint of all these lines joining the nearest neighbor, and this is the region you can check for yourself which is closer to the central point than from any other point. So, that would be the Wigner Seitz cell for this. So, that is the region which is closer to this central point than to any other point. So, that is what it is. So, you do it in the reciprocal lattice, and then that is what is called the Brillouin zone. To calculate the Wigner Seitz cell for honeycomb lattice, this is a problem we have given somewhere. So, try to work it out. If you cannot, the answers are given. So, you will see the answer. Oh, pattern of exam, of course, this is important. The pattern would be the same as we are using for our homework problems. We will give multiple choice type problems, where you have to solve the problem and tick the right answer. So, that would be it will be online, so you will be able to you will be able to answer, get it done online. You have very good friends in Ravi and Shubham. So, you can ask your questions over email to them also, they will answer, but do not please ask questions which are asked as a homework, they will not solve it for you, they will not even give hints for it, because it will be unfair to other students, right. So, please refrain from doing that, otherwise you can ask any questions, any doubt to us. Any more questions? No.
This is an old question from forum, since we had time. So,
how do I discard this?
so the problem in forum. So maybe you can address that.
Yeah, this is a question which was asked in the forum. In the tight binding model, for example, we had used a hopping parameter which we called minus t. Now, of course, for certain lattices like square lattice or one dimensional lattices, this sign does not really matter, but for other lattices like for example, triangular lattice, the sign matters, because as you know, there are the singularities in the density of states. So, the location of the singularity will depend on what the sign of t is. That is one issue, and then of course, the beginning of the band and the end of the band will also depend on the sign of the t. Now, the reason one puts this negative sign is that one wants to keep the value of t as positive. Now, if you look at that integral which is involved in calculating the t, which is the wave function at one side, then Hamiltonian, and the wave function at the other side, and the overlap of these with the Hamiltonian in between. So, it is a matrix element of the Hamiltonian with these two states, one at site I, another at site I plus 1 or the nearest neighbor. Now, this generally is negative. One of the reasons for that is very simple, that look at Heisenberg uncertainty principle. Heisenberg uncertainty wants in quantum mechanics, it wants I mean Heisenberg uncertainty is in quantum mechanics, it wants the particles to get delocalized. Localizing a particle costs a lot of energy, because the uncertainty in position being low in a localized state, the uncertainty in momentum becomes very high. So, the energy becomes large. So, the system actually wants to minimize its energy by delocalizing the electron, and the delocalization means you gain energy then. So, this hopping is actually delocalization of an electron, and so you gain energy. So, that is why the negative sign is it appears in the matrix element. So, t is kept positive, the value of t is always taken as positive. So, the minus sign is added explicitly to signify that this is the matrix element and its delocalization energy.
this was from forum. So,
there is one question, equation 3 of assignment 1, the solution provided consists integration of DOS equal to number density but dimensionally should it not be equal to number of particles? Numbers are always are dimensionless. So, it does not really matter, right. If you are calculating numbers, then it is it does not matter. Number of particles is the number of density of numbered density into 2 basically, because you can put see if you integrate all the states, sum over all the states, that gives you a number, multiply it by 2, that gives you the number of particles. So, it is the same. The numbers have no dimension, it is dimensionless quantity. So, going from integral of density of states to the number of particles is the same. It is in fermions, for fermions it is just a factor of 2. Actually, the density of states, when you calculate density of states, that factor of 2 is already taken in. If you look at it, then there is a multiplication by 2 that takes care of spin degeneracies. So, that is already taken in. There is a confusion over why sphere was taken to fill up the state. Yeah, it is a good question, in the sense that if you look at a free particle, the one that we are doing, then of course, the spectrum is h cross square k square by twice m, which is now if you look at a constant energy surface, E equal to E is proportional to k square, all constant energy surfaces are spheres, k x square plus k y square plus k z square equal to constant. So, that is like a sphere. So, then you have to take a sphere, so that the energy on the sphere is constant. So, all the particles on that sphere have the same energy. So, that is why a sphere is considered. This is a state question. Okay. Big fan, sir. Thank you so much. You should enjoy your course, that is all. I mean, the course is to enjoy, and these are new things you are learning, and just try to enjoy the course, that is all about it. What is ESE material science? ESE stand for what? It is useful for material science, certainly it is very useful for material science. Materials nowadays are all about this modern materials, high technology materials, but what is your ESE, please? Do you need to study quantum physics? I mean, you of course need to study quantum physics at some point, because all modern materials are based, I mean the applications are using quantum mechanics. So, you will be left behind if you do not study quantum mechanics a bit. Just do not study quantum mechanics for the sake of it. You know the basic principles of quantum mechanics, and whenever a problem comes, just try to solve the problem. Engineering services exam, of course, engineering services exam should have quantum mechanical questions from this kind of subjects, of course. I mean, anything to do with materials will ask you about band structure and so on, should ask you. So, electronic properties of solids is a major part of any material science. Look, this course is Mr. Sohadda, this was not a course for preparing you for engineering sciences exam, right. So, it is I will not cover whole of ESC, I do not even know what that syllabus is, but what I am teaching is certainly part of any material science exam or course or whatever you study. So, that is all I can say, right. I mean this is a extremely major part, this is probably the most important part of material science apart from just some physical properties, even those physical properties derive from these kind of theories. So, these kind of understandings. So, as such I cannot tell you whether it is what is the syllabus of ESC, I do not even know, and therefore, I cannot comment on that, but I suggest and I suppose that any course on material science which deals with the understanding of the material should require this kind of an understanding that is conveyed in this course.
When I told you that question about spin flipping, that two hydrogen atoms were far apart and then
Okay, there is a question about the spin flipping in this hydrogen molecule problem. Okay. So, let me just reiterate. Thank you, Showard. Thanks a lot. This question is about the spin flipping in a hydrogen molecule that I taught, starting from two hydrogen atoms which are far separated and then they were brought together. Now, this is an interesting thing that when two atoms are far away, they do not talk to each other, two hydrogen atoms, and their spins can take any direction. So, there is no preferred direction for the spin, spins can be up, can be down, it does not really matter, these are all degenerate states. So, there is nothing to choose between up and down and so on. So, this is like a paramagnetic state if you think in terms of magnetism. So, if you measure their magnetic moment, you will find 0, total moment will be 0, because the spins can point in any direction, there is no correlation between the two spins. But now you bring them closer, the two atoms, they start interacting with each other, they start talking to each other. By talking, one means that the Hamiltonian, the nucleus and the electron of one now interacts with the nucleus and electron of the other, and vice versa. So, that sets up the matrix element of the Hamiltonian between these two orbitals now become non-zero. So, then of course, that what I showed is that there are two orbitals that form out of the two orbitals. The new orbitals are one called bonding, one called anti-bonding, and the bonding is the lower one, and the lower one is occupied by 2 electrons, right. So, these 2 electrons are, if you occupy one orbital by 2 electrons, then of course, they will have to be up and down. So, this is a singlet state simply because of the Pauli principle. So, this is now a singlet state and which has no magnetism, it is like a diamagnetic in that sense. So, there is no magnetic moment that you will see. So, the spins do not flip as such, spins have all the possible directions allowed to it. When you populate one orbital by 2 electrons, then you have no choice, the electrons will just be up and down and a linear combination up down plus down up and minus down up. So, that is the singlet configuration that we discussed in the class. So, do not think of these as classical balls or classical objects with rotating up and down direction, it is not that. There is no such thing as flipping the spins, spins have all the degrees available to it, up it can be up and down. So, the population, the principle of lowering the energy requires them to go to a singlet state in the lower orbital, that means up down minus down up. At room temperature, thermal energy is 26 MeV. the electron get into conduction in case of Si semiconductor with band gap of 1.1 eV. Of course, it can the remember the factor that one talks about is sorry, let me just get to the spreadsheet. See, the Boltzmann factor is e to the power minus beta E, right, which is E by k T, and at high temperature, of course, this is what you had. Otherwise, you have the Fermi factor, this is Boltzmann. Then of course, there is Fermi factor also, which is at high temperature it reduces to the same, but otherwise it is e to the power minus beta E plus 1. Now, in either of these cases you will see that there at any temperature which is non-zero, suppose you have a gap like this and this is as you said, this is 1.1 EV, 1.1 EV this gap, and the thermal energy is extremely low, 0.2 say 26 MeV. Okay. So, of course, if you think classically, there is no way you can go up there, because the energy required to go up there is 1.1 EV, but this is not a classical system. So, now if you put these numbers in your Fermi function, then you will see that there is always a finite number that is available here. So, it is never 0. So, that is exactly what happens in quantum mechanics, that there is always at any finite temperature, as long as beta is not infinity. See, if beta is infinity, then there is no way it can go to the upper level, but as long as beta is finite, there is a probability that you will always find some electrons in the upper level. Very few, depends on the amount of thermal energy you are giving, but it is non-zero. So, as we remember the Fermi function we plotted at 0 temperature it is like this, but at finite temperature there is it goes above. So, there are always finite probabilities that you will be above the gap. So, that is about it. So, in place of E you can put the gap which is 1.1 electron volt, in place of beta you put 1 over 26 MeV, and then you will find that this number is no longer 0, and that is it. So, that means there is a finite probability of an electron jumping up to the upper level, or that means if you have 10 to the power 23 electrons, a fraction of that will be at the upper level at any finite temperature. Oh, I really Mr. Shrutar, what is this question? It leaves behind a hole in the valence band, which is correct, but in case of n type or p type at the donor level, electron goes to conduction band of n types. No, I do not understand what you are saying. The first part is correct, that it leaves behind a hole in the valence band. It leaves an immobile ion in the donor level. Ions are not in any level, ions are ions. I mean, they are not part of the level or anything. The level that you are talking about is electronic states, and whenever you take out an electron from any level, any states, it will leave behind a hole. So, ion, do not think about an ion, ion is already gone. I mean, once you are talking about the valence and conduction bands or the impurity band, there is no such thing as ion, ion is gone, ion has nothing to do with it, the ion only supplied that electron. No, again it is the same problem, I think you are. Huh?
He means holes.
But it leave an ion in donor level.
He means to leave hole in the valence. He means to say hole.
Do you mean to say hole in the valence band, which is correct? See, an ion in donor level makes no sense. No? The ion is an ion. I mean, ion is not in the in donor level. You are probably meaning that there is a hole that is left behind in the valence band, which is correct. Once you raise something from, you take an electron from valence band, put it in the conduction band, you will leave a hole in the valence band. That is correct. You transfer electron from valence to conduction band, leaving behind a hole in the valence band, that is perfect. Do not bother about the ion is not in any level. Ion is just a big classical object, almost a classical object. So, it is not part of your conduction or valence band or anything, only the electrons form these bands. This band bending we have not discussed so much, but band bending is basically that when your band reaches a surface, then of course, the band there is an infinite potential barrier there, right, the particles are confined there. So, that means the band reaches that hits that infinite potential barrier, it gets it has to go up. So, that is what is called the band bending. So, it is like you are putting a potential there which is very large at the surface, because the particle cannot escape. So, that means the band has to bend there. You can bend a band by putting a constant potential also, that is also done by putting the gate potential and so on. So, it is just basically the sum of this band energy and the additional potential energy that is there. It can come from the gate potential, or it can come at the surface where there is an infinite potential. So, any constant electric field will give you a linear potential, right. So, it is just a flat potential plus a linear potential will give you a triangle like situation, which is again will bend the band. So, that is what happens in if you put a constant field from the gate, and at the surface of course, at the edge you have an infinite potential sitting, because electrons cannot escape the surface. So, the band at that point also has to bend. So, bending of band just means that this additional potential bends the band. Look at your lecture notes where we discuss the band bending in in a FET geometry. There it was done using a constant electric field. At the surface the potential itself has a huge value. So, either way you will get a band bending. Thank you so much. Oh, this next person has come.